This is problem 625 in Smith and Van Ness, 8th edition. In this problem, we have steam at 2100 kilopascals in 260 degrees C expands at constant enthalpy, so a throttling process, to 125 kilopascals. They ask us, what is the temperature of the steam in its final state and what is its entropy change? And then a second part, what would the final temperature and entropy change be if it were an ideal gas? So this problem, I think the easiest thing to do first would be to look at the last question where they ask what would happen if we treated the steam as an ideal gas. And so hopefully you could answer that at least as far as the temperature goes right away. What would that be? Well, a throttling process is what? That's where we're simply just opening a valve. There's no work. We usually assume it's adiabatic. We neglect kinetic energy, potential energy changes. And so all we have is delta H, and delta H is equal to 0 for a throttling process. That's the definition of a throttling process. For an ideal gas, enthalpy is a function of temperature only, right? And so for an ideal gas, if there's delta H is 0, then the temperature has no change. And so for an ideal gas, we consider this as an ideal gas. The steam coming out would be at 260 degrees C. So what we're going to do is we're going to do this problem treating steam as a real fluid and see what the deviations from ideal gas behavior are. Now, remember in chapter 6 we looked at ways to calculate delta H's for real fluids. One of the ways is to use residual properties, where we take our real fluid, we go down to an ideal gas state at those conditions. We then make the change, our process change, as an ideal gas, and then we go back to the real state at the T2P2 using residual properties. We're not going to do that. I mean, we could if we really wanted to, but we don't have to because we've got steam tables. Property tables are almost always going to be maybe not easier, but at least more accurate and probably overall just as easy. The main thing with property tables is you got to spend a lot of time interpolating if the problem isn't written just right. So again, put our beginning information in just to set things up and make a little table for our beginning and final conditions. MathCAD, the version I'm using, does not use degrees Celsius, so all temperatures need to be in Kelvin, which for thermo isn't bad to begin with, but we don't know what T2 is. This is what we want to calculate. And so just to remind ourselves, what we want to find is we want to find T2, and we want to find the change in entropy, and then we want to compare it to what we have for ideal gas behavior. And so this just says what I talked about earlier. We should use steam tables. Property tables are going to be more accurate. We may need to do some interpolation, but remember, if we have our handy-dandy little interpolation worksheets, we don't have to spend lots and lots of time punching things into calculators. We can just paste in our interpolation template and change a few numbers and hopefully be on our way. So the question is, what kind of steam do we have here? Is it saturated steam? Is there a mixture of liquid and water? Or is it superheated steam? And the way the problem is written, we probably have superheated steam, but what you want to do, you want to make sure that you know what you're dealing with, and so you can check this. And so you can see, if we look at in our saturated steam tables, we have at 260 degrees C, our saturation pressure is 4694 kilopascals. That's a lot higher than what we're dealing with, and so we know that we have superheated steam. We know that this is a throttling process, so delta H is 0. And so what we will do is we will use that information to figure out what the outlet temperature is and then calculate delta S. So we know P1, we know T1, and we can look up the enthalpy for state 1, right? We know that enthalpy is equal to enthalpy change is equal to 0. So we know that H2 has to be equal to H1, right? So if we know that, we don't know what our temperature is, so we don't know where to look at the steam tables just from pressure. It could be anything. But if we know pressure, we know enthalpy, we can then look up what the temperature is. And then, of course, we can calculate delta S because we can then look up entropy and calculate the change from state 1. So that is how we're going to solve the problem. So go to the steam tables, look it up at 2100 kilopascals. This is superheated steam tables. Page 705 is where you'll find the value for that. And so we need to look up both the enthalpy and the entropy values at 260 degrees C. But what you see is at 2100 kilopascals on page 705, you'll see that you only have entries at 250 and 275. So what we're going to have to do is we're going to have to do some interpolation. So get your interpolation spreadsheet or MathCAD worksheet, and I'll just bring this over here. So X is my independent variable, that's temperature. M is my dependent variable, that is enthalpy. So I enter those values in. I want to calculate the enthalpy at 260. You can see here I'm not using any units. It just takes time typing in units for everything. You don't have to, as long as you're keeping track of what you do. Your value M that you get out of this will be unitless, and so then I just assign it H is equal to M times kilojoules per kilogram. So I put my enthalpy in there, my units into my enthalpy, so that I can use it directly in my subsequent calculations. Another thing that I would caution you is be very careful as you read these values from the steam tables. The thing about units, so for enthalpy, internal energy, and entropy, everything is kilojoules per kilogram. So kilojoules and kilograms, and then remember you have per Kelvin in the base in the denominator of the unit for entropy. The units for volume are centimeters cubed per gram. So again, this is a nice, it's not as bad doing the conversions when you're dealing with MathCAD, using MathCAD to do your calculations, because you don't always have to be converting centimeters cubed per gram to meters cubed per kilogram, which is just kind of a pain to have to do every time if you're doing these calculations by hand, or even if you're doing these calculations in a spreadsheet. So again, this is why I strongly encourage you to use MathCAD. It's just going to make life a lot easier for you on these quizzes and exams. So anyway, this is our enthalpy of our initial at our initial state. All right. Now what we need to do is I'm going to go ahead and just, while we're at this initial state, I'm going to go ahead and calculate my entropy. And so I need to set up another interpolation of that, single interpolation of that. And so what I can do is just take this, directly copy and paste it, and just change the values of entropy. And again, I'm not using units in my actual calculation here, but I add the units once I get done so that I can directly use S1 in my calculations. The other thing that I want to mention is when you read these values off in the tables, be careful. These tables go across the page, and there's lots of entries. I don't know if your eyesight is as good as mine. It's probably a lot better, but I always have a straight edge. I always use a straight edge. Even when I was a student, I used a straight edge, just a piece of paper or something like that that's folded so that you make sure that as you read across that entire width of your length of your textbook, that you're not moving up or down and copying the wrong value. That's going to really mess you up. So spend some time, a little bit of time. You've got plenty of time to do all these problems at home to make sure that you copy things correctly from these tables. The print is small, lots of values. It can kind of be a pain to work with, but if you're careful, you can do it. So now we can start solving the problem. All right, now we can start solving the problem. So we know that our pressure at the outlet is 125 kilopascals. And so what we need to do then is we go to this 125 kilopascal entry in the steam tables, and we find where do we get an enthalpy value that is equal to H1, 2924 kilojoules per kilogram. And so if we go through there, and I'll do this a little slowly, you can follow along, you can pause and follow along if you like. We go to page 693, and we see that at a pressure of 125 kilopascals and a temperature of 225 degrees C, we see that our enthalpy is 2923.9 kilojoules per kilogram. And remember, what our goal was is to find out where the enthalpy was 2924 kilojoules per kilogram. So I'm going to assume in doing this problem that this is close enough. I mean, you do need to know how to interpolate, but we're talking about decimal, hundredths of a percent here as far as the difference in values. So if you'd really like to interpolate, you can do that. But I'm just going to say that our final temperature based on the steam tables is going to be 225 degrees Celsius, or make sure I put the 0.15 in, or 498.15 Kelvin. All right. So that is our final temp. That's the temperature of our steam coming out. So remember, what did we do? There's a lot of clutter here as far as all the math that we have to do. But remember what we did. This is a throttling process. And so we figured out what our enthalpy of our inlet is. We know that for a throttling, our enthalpy change is 0. So it's the same enthalpy value, but we're at a lower pressure. And so what I have to do then is I have to go to my steam tables and I have to say, okay, at 125 kilopascals, where is the enthalpy equal to 2924 kilojoules per kilogram? So this is just straight hunt and find. All right, you just look at the column of 125 kilopascals, and you look to see where do I get 2924. We were pretty lucky here in that it was very, very, very close to one of the direct entries in our steam table. But what if it happened to be different? So we're going to have to look at where, if it didn't work out so well, we'd have one value here, we'd have another value here that would be in between, and then we would have to do the interpolation, right? And we found that was at 225 degrees C, or 498 Kelvin. All right, so what we can do then is we can just look up. Remember, the next thing we have to do is calculate our delta S. So we're just going to assume, again, 225 degrees C. We look up the value for delta S, for S2. That's what we get. We calculate delta S and we get 1.268 kilojoules per kilogram Kelvin. So these are the answers: 498.15 Kelvin, or 225 degrees C, and 1.268 kilojoules per kilogram Kelvin. That's the answers to the first part. Now the rest of the problem, we've already kind of answered some of it, is how would this be different if it were an ideal gas behavior? And so we already said that if this were an ideal gas, enthalpy is a function of temperature only. There's no change in enthalpy, so that means that there cannot be any change in temperature. So our outlet temperature would be the same as the inlet temperature, all right? But as you can see, for the real case, we have a different outlet temperature. It is 498 Kelvin. There's a 35 degrees C difference in our real case. So in this case, for temperature calculation, the ideal gas is not a good approximation. What about for the enthalpy change? How does that compare? Well, for an ideal gas for an entropy change, remember it's delta S is equal to Cp log of T2 over T1 minus R log of P2 over P1. But since T2 is equal to T1 for an ideal gas, right? Remember, for an ideal gas, there's no change in temperature. So T2 is equal to T1. All we're left with is minus R log of P2 over P1. And so we can do the calculation. And we do that in kilojoules per mole. Water is 18 grams per mole. Our value up here was in kilojoules per kilogram. And we do the conversion to mass-based units, and we get 1.30. So 1.30 versus 1.27. That's not that much of a difference. So temperature-wise, there's a big difference between ideal gas and real behavior. But when we're calculating delta S, there's not that much of a difference. So just to finish up this problem, what makes steam at these conditions a real gas versus an ideal gas? These are things that you should think about. I would encourage, it's not a requirement for necessarily for this part of the class, but especially when you get into your next semester of thermodynamics, you're really going to have to deal with this. And the sooner you start thinking in this way, the better. What makes steam at these conditions a real gas versus an ideal gas? Well, one of them is just the high pressure. Remember, ideal gas is valid in the limit as pressure goes to zero, where we have essentially no intermolecular interactions. There's no collisions between our gas molecules. And then secondly, remember, ideal gases have no attractive or repulsive forces. Steam, water molecules have very strong hydrogen bonding. And so that's going to affect the behavior of a real gas. So that's how we do this problem. This problem was just a very simple first law problem. In chapter 3, we would have solved this and just said delta H is equal to 0, T2 is equal to T1. That would have been it. In chapter 5, we would have said T2 is equal to T1, delta S is equal to minus R log P2 over P1. That would be it. Here we have a real problem, a real gas, and we're not going to use residual properties yet. We're going to use property tables. We do our calculations. The only thing that really complicates these calculations is having to do so much interpolation. So as you work these problems, try not to get bogged down in the details of the interpolation, all right? It's gonna, if you were working this with pen and paper and a calculator, this would take a long time. But what you should do is you should have your interpolation worksheet open, say in another window or on another screen, and just be able to copy and paste this in very quickly. These should just become very quick calculations that end up not taking you that much time. You really want to focus, as you're doing these problems, you really want to focus on the actual thermodynamics calculations that you're doing and making sure that you're applying the first law and the second law properly to get your answer. And then, as an added bonus, once you get the answers, start thinking about the problems in terms of how our system is deviating from ideal behavior.